But then, there's this story that you will hear, that Einstein couldn't quite cope with quantum mechanics, right? The world of physics has long been defined by the towering achievements of Albert Einstein. His theory of relativity redefined our understanding of space, time, and gravity, giving us the tools to explore the cosmos. For over a century, his work has stood as a cornerstone of modern science. But recent advancements in quantum computing are shaking the very foundations of physics and challenging some of Einstein's most cherished principles. It's not just that quantum computers are faster than classical machines. These devices operate on principles so strange, so counterintuitive, that they are forcing scientists to reconsider what we thought we knew about reality. And the implications they bring are nothing short of revolutionary. Let's begin by unpacking what quantum computers are, and why they're so different from the classical computers we've used for decades. Traditional computers process information in bits, which can be either a 0 or a 1. This binary system is the backbone of everything from smartphones to supercomputers. But quantum computers use qubits, or quantum bits. A qubit isn't just 0 or 1. Thanks to the principle of superposition, a qubit can exist in multiple states simultaneously. Imagine flipping a coin, but instead of landing on heads or tails, it lands on both at the same time. This ability to be in many states at once allows quantum computers to process massive amounts of data simultaneously, solving problems that would take classical computers millions of years to compute. And it doesn't stop there. Another key feature of quantum computing is entanglement. When qubits become entangled, the state of one qubit is instantly linked to the state of another, no matter how far apart they are. Change one, and the other changes as well, as if by magic. Einstein himself famously referred to this phenomenon as spooky action at a distance, and it was something he struggled to accept. Einstein believed in a universe that was orderly and deterministic. He famously said, "God does not play dice with the universe." But the principles of quantum mechanics suggest otherwise. At the quantum level, reality is probabilistic, not deterministic. Events don't unfold according to a fixed script. They happen based on probabilities. This fundamental randomness defies the very essence of Einstein's worldview. For decades, these quantum principles were confined to the theoretical realm, debated in classrooms and research papers, but with little practical application. That's no longer the case. With the advent of quantum computers, we are now harnessing the bizarre rules of quantum mechanics to solve real-world problems, and the results are challenging some of the most fundamental assumptions in physics. One of the most groundbreaking revelations comes from quantum computers' ability to simulate quantum systems. Classical computers struggle to model complex quantum interactions because the math becomes exponentially harder as the system grows. But quantum computers thrive in this environment. They can simulate quantum systems with stunning accuracy, allowing scientists to test theories and perform experiments that were previously impossible. Here's where things get really interesting. In 2023, researchers used quantum computers to simulate certain quantum phenomena that didn't align with Einstein's equations of relativity. These simulations revealed discrepancies in how quantum particles interact with spacetime at incredibly small scales. Einstein's theory of relativity works exceptionally well for large-scale systems like planets, stars, and galaxies. But when you zoom into the quantum level, the rules start to break down. Space and time, which Einstein described as a smooth, continuous fabric, appear to be discrete and fragmented at the smallest scales. Quantum computers have provided the first direct evidence that spacetime may not be the smooth continuum Einstein envisioned, but rather a pixelated structure, like the resolution of a digital image. This idea isn't entirely new. The concept of quantized spacetime has been explored in theories like loop quantum gravity, but until now there was no way to test these ideas. Quantum computers are changing that. They are giving us the tools to explore the quantum structure of space-time, potentially rewriting our understanding of the universe. Another area where quantum computing is challenging Einstein's legacy is in the realm of causality. In classical physics, cause and effect are straightforward. One event leads to another in a clear linear sequence. But quantum mechanics suggests that causality isn't always so clear-cut. Quantum computers have demonstrated phenomena known as indefinite causal order, where the sequence of events becomes blurred. Imagine two events, A and B. In the classical world, A happens first, then B. But in the quantum world, A and B can occur in a superposition, where neither clearly happens before the other. This defies our classical understanding of time and causality, concepts that were central to Einstein's theories. The implications of this are profound. If causality can be indefinite, it raises questions about the very nature of time itself. Is time a fundamental property of the universe, or is it an emergent phenomenon, a byproduct of deeper quantum processes? These are questions that quantum computers are helping us explore, and the answers could reshape our understanding of reality. Perhaps the most shocking revelation of all is the potential connection between quantum computing and the nature of consciousness. Quantum mechanics has long been associated with the mysteries of the mind, from the observer effect to the role of consciousness in collapsing quantum wave functions. Some researchers are now using quantum computers to explore these connections in unprecedented ways. One theory suggests that consciousness itself might be a quantum phenomenon arising from entangled networks of neurons in the brain. Quantum computers could help test this idea by simulating the quantum processes that might underlie thought and perception. If true, this would not only revolutionize neuroscience, but also challenge our understanding of identity, free will, and the nature of existence. The advent of quantum computing also raises practical and ethical questions. For one, the sheer power of quantum computers could render classical encryption methods obsolete. Current cybersecurity protocols rely on the difficulty of factoring large numbers, a task that would take classical computers millions of years. But quantum computers could crack these codes in seconds, potentially exposing sensitive data and creating a cybersecurity crisis. On the flip side, quantum computers also offer solutions. Quantum encryption methods, such as quantum key distribution, are virtually unhackable. These systems use the principles of quantum mechanics to ensure that any attempt to intercept or tamper with data is immediately detectable. Then there's the question of how quantum computing will impact the global balance of power. Countries and corporations are racing to develop quantum technologies, recognizing that whoever controls this technology will have a significant strategic advantage. The quantum arms race could redefine geopolitics in the 21st century, much like the space race did in the 20th century. As we stand on the brink of this quantum revolution, it's clear that the implications extend far beyond science and technology. Quantum computing is forcing us to confront deep philosophical questions about the nature of reality, the limits of human knowledge, and our place in the universe. Einstein's contributions to physics will always be monumental, and his theories remain incredibly useful for understanding the macroscopic world. But quantum computing is revealing that his vision of the universe was incomplete. The quantum world is far stranger and more complex than Einstein could have imagined, and we are only beginning to scratch the surface. This isn't just about proving Einstein wrong. It's about building on his legacy to uncover deeper truths about the cosmos. As quantum computers continue to advance, they will undoubtedly challenge more of our assumptions and push the boundaries of what we thought was possible. The question isn't whether Einstein was wrong. It's what new doors his ideas have opened for us to explore. The quantum revolution is here, and it's changing physics, technology, and our understanding of reality forever. Quantum computing is more than just a technological advancement. It's a paradigm shift in how we view the universe. In this expanded discussion, we'll explore the quantum revolution's ongoing scientific breakthroughs, how they intersect with Einstein's foundational ideas, and the ripple effects across disciplines like cosmology, biology, artificial intelligence, and even ethics. Quantum computing, bridging the classical and the quantum worlds. One of the most remarkable aspects of quantum computing is its ability to connect two seemingly incompatible views of the universe: the deterministic world of classical physics and the probabilistic realm of quantum mechanics. Einstein's theories, particularly general relativity, are grounded in a deterministic framework. Spacetime is a smooth, continuous fabric, and the movement of objects through this fabric follows predictable causal rules. Quantum mechanics, however, operates on entirely different principles. At the quantum level, particles behave like waves, existing in multiple states simultaneously until observed. This duality and probabilistic nature make it challenging to reconcile quantum mechanics with the smooth, deterministic nature of general relativity. Quantum computing provides a unique bridge between these worlds. By simulating quantum systems on an unprecedented scale, quantum computers allow us to explore the boundary where classical and quantum physics meet. This is where some of the most fascinating and groundbreaking discoveries are happening. For example, researchers are using quantum computers to simulate black holes and other extreme environments where quantum mechanics and general relativity collide. Black holes, with their immense gravity, warp spacetime to the breaking point, creating conditions where Einstein's equations are no longer reliable. Quantum computers can simulate these conditions, offering new insights into phenomena like Hawking radiation and the mysterious information paradox. The information paradox, first proposed by Stephen Hawking, arises from the conflict between quantum mechanics and general relativity. When matter falls into a black hole, its information should, according to quantum mechanics, be preserved, but Einstein's equations suggest that this information is lost forever. Quantum simulations are helping scientists unravel this paradox, bringing us closer to a unified theory of quantum gravity, a theory Einstein himself pursued but never achieved. The quest for quantum gravity. At the heart of the quantum revolution lies the search for quantum gravity, the elusive theory that would reconcile general relativity with quantum mechanics. Quantum gravity seeks to describe how gravity behaves at the quantum level, uniting our understanding of the very large and the very small. Einstein's general relativity describes gravity as the curvature of spacetime caused by massive objects. This framework works exceptionally well for predicting the behavior of stars, planets, and galaxies, but at the quantum scale, spacetime is not smooth, it becomes granular and probabilistic. Quantum gravity aims to explain how these quantum fluctuations of spacetime give rise to the macroscopic gravitational effects we observe. Quantum computers are playing a pivotal role in this quest. By simulating quantum fluctuations in spacetime, researchers are uncovering patterns and behaviors that were previously inaccessible. These simulations suggest that spacetime itself may emerge from more fundamental quantum processes, challenging Einstein's view of spacetime as a continuous fabric. One particularly exciting development comes from the holographic principle, a concept rooted in string theory. The holographic principle suggests that our three-dimensional universe is a projection of information encoded on a two-dimensional surface. Quantum computers are now being used to test this idea, simulating holographic models of spacetime and revealing new insights into the nature of reality. If spacetime is indeed holographic, it would fundamentally alter our understanding of the universe. It would mean that the reality we experience is not the fundamental layer of existence, but rather an emergent phenomenon, a kind of cosmic illusion. The role of quantum entanglement in the universe. Quantum entanglement, the spooky action at a distance that so troubled Einstein, is emerging as a central player in the fabric of reality. Recent research suggests that entanglement is not just a peculiar feature of quantum mechanics, but a fundamental building block of the universe itself. Physicists are exploring the idea that spacetime may arise from a vast network of entangled particles. This concept, often referred to as quantum geometry, suggests that the structure of the universe at the smallest scales is defined by the entanglement relationships between particles. Quantum computers are uniquely suited to model these relationships, providing a new lens through which to view the origins of space and time. One groundbreaking experiment involved creating a quantum wormhole using entangled particles. Wormholes, theoretical shortcuts through spacetime, are a staple of science fiction, but recent work has shown that entanglement could create structures analogous to wormholes, connecting distant points in spacetime. Quantum computers are being used to simulate these wormhole-like structures, offering tantalizing clues about the interconnected nature of the universe. If entanglement truly underpins spacetime, it raises profound questions about the nature of reality. What we perceive as distance, separation, and even time itself may be emergent properties of a deeper quantum network. This idea challenges Einstein's conception of a deterministic universe and opens the door to a new understanding of existence. Quantum computing and the arrow of time. Time is one of the most mysterious aspects of reality. In Einstein's theory of relativity, time is a flexible dimension intertwined with space and affected by gravity. But in the quantum world, time behaves very differently. Quantum mechanics suggests that time may not flow in a single direction. Instead, quantum systems can exhibit time symmetry, where processes can run forward or backward with equal probability. Quantum computers have demonstrated this phenomenon in experiments, effectively reversing the arrow of time in controlled systems. This challenges one of the most fundamental assumptions in physics, that time is a one-way street. The arrow of time, as we experience it, is closely tied to the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases. But quantum experiments suggest that entropy can decrease in isolated quantum systems, at least temporarily, defying classical expectations. These findings have profound implications for our understanding of time, causality, and the nature of the universe. If time is not a fundamental property of reality, but rather an emergent phenomenon, it raises questions about the origins of the universe and the possibility of manipulating time in practical ways. Quantum biology, a new frontier. The impact of quantum computing extends beyond physics into other scientific disciplines, including biology. Quantum mechanics plays a surprising role in biological processes, from photosynthesis to human cognition. Quantum computers are helping scientists uncover these connections, revealing a new field known as quantum biology. One of the most intriguing examples is photosynthesis, the process by which plants can convert sunlight into energy. Research has shown that quantum coherence, the same principle that allows qubits to exist in multiple states, enables plants to transfer energy with near-perfect efficiency. Quantum computers are helping researchers model this process, potentially leading to breakthroughs in renewable energy. Quantum mechanics may also play a role in the human brain. Some scientists hypothesize that quantum processes occur within microtubules, tiny structures inside neurons. If true, this could explain the brain's remarkable computational power and provide insights into the nature of consciousness. Quantum computers are being used to test these ideas, offering a glimpse into the quantum underpinnings of life itself. Ethical and philosophical implications. As quantum computing continues to advance, it raises profound ethical and philosophical questions. What does it mean to live in a universe where reality is fundamentally probabilistic and interconnected? How do we reconcile the deterministic laws of classical physics with the randomness of the quantum world? One of the most pressing ethical concerns is the potential for misuse. Quantum computers have the power to break classical encryption, potentially exposing sensitive information and destabilizing global security. Governments and corporations are racing to develop quantum-resistant encryption methods, but the stakes are high. Another concern is the impact of quantum technology on privacy. Quantum sensors, which exploit the principles of quantum mechanics, could revolutionize surveillance by detecting minute changes in the environment. While these sensors have legitimate applications, such as earthquake detection and medical imaging, they also raise concerns about privacy and the potential for abuse. Philosophically, quantum computing challenges our understanding of free will and determinism. If the universe is fundamentally probabilistic, what does that mean for human decision-making? Are our choices truly our own, or are they the result of quantum processes beyond our control? These questions go to the heart of what it means to be human. Quantum computing doesn't just challenge Einstein's theories. It challenges our deepest assumptions about reality, identity, and existence. The future of quantum computing. As we look to the future, it's clear that quantum computing is just beginning to reveal its potential. Advances in hardware, algorithms, and experimental techniques are accelerating at an unprecedented pace. One of the most exciting developments is the concept of quantum supremacy, the point at which quantum computers can perform tasks that are impossible for classical machines. In 2019, Google claimed to achieve quantum supremacy with a 53-qubit processor called Sycamore. While the task it performed was relatively simple, it marked a major milestone in the field. Since then, researchers have continued to push the boundaries, developing larger and more powerful quantum processors. The ultimate goal is to create fault-tolerant quantum computers capable of performing complex calculations with high accuracy and reliability. These machines could revolutionize fields ranging from cryptography and material science to medicine and artificial intelligence. Quantum computing represents a new frontier in science and technology, one that challenges the very foundations of physics as we know it. Einstein's theories remain monumental achievements, but the quantum revolution is revealing the limitations of his deterministic worldview. As we continue to explore the strange and interconnected quantum universe, we are uncovering new layers of reality, reshaping our understanding of time, space, and existence itself. The journey is just beginning, and the possibilities are as infinite as the universe. Quantum computing isn't just a technological breakthrough. It's a window into the mysteries of the cosmos, a key to unlocking the secrets of existence, and a testament to the power of human curiosity and innovation.